The next concept we want to discuss is about approximate integral. The idea is to find the integral approximately because sometimes we may not be able to integrate. For example, this function is hard to find the exact value of this guy because e to the minus x square has no elementary antiderivative and hence you can't integrate it. We have already seen some of the approximate integral. Most of it we are going to formalize in this chapter. So remind yourself about the following. Let f be a continuous function on a closed interval ab, and ab is divided into n subintervals. Let's call those intervals as x0, x1, x1, x2, x2, x3, x4, x5, so on, xn minus 1 to xn, which is b. And each is of equal length, say delta x. That need not be the case though in general, all right? In real life application, that need not be the case. However, let's take them of equal length. Then integral a to b fx dx is roughly equal to summation I going from 1 to n f of xi star delta x, where xi star is some point in xi minus 1 to xi. Yeah. So the idea is that this integrals, this is approximately equal, right? I mean, like an approximation again is a big approximation depends on the user, right? I mean, like it depends on who defines the approximation. So what we are doing is we are dividing it into n intervals of equal length, each of width. So we are making rectangles again. We have b minus a by n, and we are choosing some point xi star here. Then we go and we basically make a rectangle like that, and we basically approximate it by this area here. Yeah. And of course, it's not going to be it becomes equal to exact area under the limit, but since we are doing approximate integral, for sufficiently large n, you will find an approximation. Okay. So now we have to find the ways to choose this sample point xi star, right? Because after all, this is approximation and we need a way to choose these xi stars. So one way is to choose xi star to be the leftmost point. Other way to choose is choose xi star to be the rightmost point. We have already dealt with this when we are looking at the left-hand sum and the right-hand sum. So let's formalize this. So endpoint approximation. If you use the left point approximation ln and right point approximation rn is given by what? You take delta x, which is this width here. So in this case, I've taken n to be 4. So there are 4 intervals. So in this interval, now for the height, I'm choosing my x1 star is this point, right? So I go, what is the function value is here, and then I go and draw a rectangle like that. Then for this interval, I'm choosing what? The left-hand point is this guy here, and then I'm drawing the rectangle and taking. For this interval, I'm choosing the left-hand value of this function on the interval and then making a rectangle and adding them, so on and so forth. Similarly, we can have the right-hand point approximation. So if you take an interval, in this case, you will go and see what is the value of function on the right-hand point, which is x1 on this interval, and then make a rectangle that and add all of these guys up. So if I want to write ln is simply summation I going from 1 to n f of, instead of xi, you're starting with this point. So xi minus 1 delta x. And your Rn is going to be summation I going from 1 to n f of xi delta x. So this is with n equals to 4. So this is an approximation. This is one kind of approximation we have already dealt with. Now, instead of choosing ln or rn, what if we, instead of choosing the right hand or left hand point, we choose the midpoint. So we get a midpoint approximation. So what we do is we basically take x0 to x1, take the midpoint of this. So the midpoint of this is somewhere here. And then you basically use that midpoint for the height. So you use, as you can see, we have chosen that midpoint for the height. So we get a rectangle like that. Similarly, for this guy also, we chose the midpoint that gives us the height of the rectangle, and the width is already given to you. And you add all of them. So generally, often the idea is, if your function, depending on the function, often the error is less than ln and rn. Yeah, because you think about it as function as balanced on both sides, right? Little bit here on this side, little bit bigger, little bit smaller. So it kind of balances out. But it depends on your function, the shape of the function. So this is called midpoint approximation. Yeah. Again, what is the idea? The idea is, again, you're doing summation I going from 1 to n f of delta x. So this part remains same for all kind of approximation. Here we are choosing what? The midpoint. So we are choosing, let's call this as xi bar, where xi is midpoint of midpoint of xi minus 1 and xi, right? So this is what the xi bar is, and you know what is the midpoint is. Just take these two values and take the average, right? So this is what is called midpoint rule or midpoint approximation. Similarly, we can have so now the next approximation is what is called trapezoid rule. So what you do in trapezoid rule is, instead of approximating as a midpoint, you take these points, so x0 to x1, you basically go at this points and form a trapezoid. So you join these two guys and you get a trapezoid like that. Now, what is the area of a trapezoid? So area of a trapezoid is, so area of this trapezoid, for example, is going to be what? Half base width, which is delta x, times the sum of the height. So which is going to be, if this point is f of x0, the value y value here is f of x1, then it's going to be f of x0 plus f of x1. This is the area of one rectangle. Yeah. So if you add all of them up, you get what? You get delta x by 2. For the first trapezoid, you get f of x0 plus f of x1. For the second trapezoid, what will you get? You will get f of x1 for the first trapezoid. For the second trapezoid, we'll get f of x1 plus f of x2. So on and so forth. For the last trapezoid, you will get f of xn minus 1 plus f of xn. And you see everything in between gets doubled, right? And the side ones are exactly ones. So therefore, the trapezoid rule gives us overall area is delta x divided by 2 times what? So you double the center one. So you double the everything in between. So the first one and the last one remains as it is because they don't get repeated, but everything in between gets repeated. So 2 times f of x1 f of x2 dot 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 f of xn minus 1, and these guys get doubled, right? So we have doubled. Let me just use a different color so that it's clear that these guys are getting doubled. And then the other extreme ones are 1. Now let's do this problem. So calculate an approximation to the integral 0 to 3 x squared dx with n equals to 6, delta x equals to 0.5 using left point approximation, using right point approximation, midpoint rule, and trapezoid rule. So let's basically do this. So your n is 6. So you have 0 to 3. And n is 6. Therefore, how many intervals? So you're going to divide it into 6 intervals. 0.5, 1, 1.5, 2, 2.5. Yeah. So what is your L6? Your L6 is going to be summation I going from 1 to 6 f of xi minus 1 times delta x. Yeah. So it's a good idea to write it in the expanded form. So it's going to be 0 square times 0.5 plus what? Plus 0.01 plus 0.5 square times 0.5. So these are your delta x's, right? So these are your delta x. This 0.5 are your delta x. These are your f of x values, right? F of x 0. This is your f of x1. So plus 1 square times 0.5. This is your f of x2. Plus 1.5 square times 0.5 plus 2 square times 0.5 plus 2.5 square times 0.5. So it would have been a good idea to take 0.5 common right away to start with. You have 0.5 square plus 1 square plus 1.5 square plus 2 square plus 2.5 square. And that turns out to be, if we do, 6.875. And clearly from the shape of the graph, how does x square looks like? So x square is like that. You are doing an, if you're using that, you're doing an underestimate, right? So this is an underestimate. Similarly, what is R6? So using right hand points, it's going to be again 0.5, but this shifted. So we have 0.5 square plus 1 square plus 1.5 square plus 2 square plus 2.5 square plus what? Plus 3 square. So this is basically adding to this guy half of 3 square, which is basically going to be 11.375. And clearly this is an overestimate. Although your problem is not asking you to underestimate or overestimate, but just giving, we are just getting an idea. That's an overestimate. Now, what about, so what is the actual value of this integral? So let's just find that. This is going to be x cubed by 3, 0 to 3, which is going to be 1 by 3 times 9. Sorry, 1 by 3 times 27, which is going to be 9. So now we can compare directly, right? That this came out to be an underestimate because less than 9. This came out to be an overestimate, which is greater than 9. Now, what about M6? So M6 is 0.5 again. Now, now you need to take a midpoint of these guys. So midpoint of this. So midpoint of that is what? 0.25 square. So we have 0.25 square. Midpoint of this guy is 0.75 square. Then the next one midpoint is 1.25 square. Then the next one is 1.75 square plus 2.25 square. And the last one is 2.75 square. I'm going to use my calculator here. And actually the area turns out to be 8.39375. So again, this is an underestimate. Okay. Now let's do the same computation with, so this was midpoint, now trapezoid, right? So in this case, what do you have? Remember the formula. So it's going to be T6 is going to be delta x by 2. So 0.5 divided by 2. So first one will remain as it is. Everything in between gets multiplied by 2, right? So 2 times 0.5 square, so what? 1 square plus 1.5 square plus 2 square plus 2.5 square. And then the last one, you add as it is, so 3 square. Yeah, so everything in between gets multiplied by 2. The last ones do not get multiplied by 2. So when you work this out, you get 9.125, which is an over. Now you saw that in each of these cases, you get an error. Some errors are better than the others in sense that this turned out to be 9.125, which was closest in some sense to the actual value, which is 9. Yeah. So note that again depends on the function. So it makes sense to discuss about how much error we got into this approximation. And again, it should depend on the nature of function, right? How the function is. So of course, the function, quite a lot about the function is determined using derivatives. So it makes sense to think about the following, that the errors will depend on the derivatives. So if E is an error using an approximation, the error is defined, this is the actual value minus the approximated value, right? That is what the error is. It turns out that the size of the error depends on the second derivative of the function, which measures how much the graph is curved. Yeah, it's meaningful, right? That the shape of the graph will determine whether it's an overestimate or underestimate, right? So these are the error bounds. This will be proved in a course, MACM 316, which is a numerical analysis course, introductory numerical analysis course. It's a very interesting course. Hopefully you'll get to take it. Which basically measures, so in numerical analysis, MACM 316, you discuss about errors and errors in different kind of computations, right? Like you did Newton's method in calculus 1, right? Newton's method was to find the roots approximately, right? How much is the error in each step? How much steps does it take to converge to the solution, right? Or for that matter, if you take matrices, you measure their eigenvalues. If you try to have an approximate eigenvalues, how much error is there? Okay, so all these questions are answered in MACM. So let's discuss the errors in each cases. So if f double prime, so consider, so you are integrating, so you are integrating f of x on a to b. And you have a method and you're approximating it either by trapezoid rule or midpoint rule. Then they depend on the following. So the error in trapezoid rule, note what is the error? Error is the difference between the actual integral and what? And the approximation you got. So error in the trapezoid rule, now it can be positive error or negative error, right? It can be more than the actual value or less than the actual value. So we'll bound the absolute value of the error. So absolute value of error in trapezoid rule is bounded by k times b minus a cubed by 12 n square, where of course a and b is clear. N is the number of, so if you divide your interval ab into, so divide ab into n subintervals of equal length, so n is known to us. Now what is k? K is an upper bound. So if you take second derivative of the function, and if you consider on AB, you need the upper bound on this. So this is basically less than equal to some k value. Yeah. Note the smaller, the closer to f double prime you have, the better bound you will get. So this gives you error in trapezoid rule. Yeah. Again, when you do the Taylor series, you can actually get this bound from the Taylor series of the function. Similarly, midpoint rule also have the following. So error in the midpoint rule is also bounded by k times b minus a cubed by 24 n squared. So just that, the difference is this one is 12 n squared divided by 12 n squared, and this is divided by 24 n squared. So let's see, for example, so what was the error in, so question from previous example, ET, the error was bounded by k times how many, what was the bound? B was here, B was what? B was, A is 0 and B is 3, right? So we get 3 minus 0 cube divided by 12 times 6 square, which turns out to be, now what is k? So we need to compute k, right? So for that, notice what is f double prime of x? So f of x is x square. So f double prime x is going to be, so 2x and then 2. So f double prime is 2. So this is bounded by 2. So in this case, we already found out k to be 2. So this is going to be 2 times 3 minus 0, which is, so 3 square divided by 12 times 6 square. This is going to be, so 1, 3, 1, 3 will cancel. So you have, so here you have 3 cube. So that 3 will cancel with this. You will get 1 over 8, which is roughly 0.125. Yeah. So this was error in the trapezoid rule. And if you look at your trapezoid rule here, you got 9.125 and the actual integral was 9. So you see the error is actually exact. Yeah. That what error we are getting here is exactly the same error in your trapezoid rule. But this may not be generally true. Now let's see what about EM. If you look at the midpoint rule, you will get this is less than equal to, again, k is 2, 3 minus 0 cube divided by 24 times 6 square, which is 1 by 16, which is going to be 0.0625. right? So, and then if you look at your answer here, you will see that this is not far. So from 9, what is 9 minus 0.89375? Yeah, so you can look at that. That is going to be what? This turned out to be 0.0625. So, which is exactly what you got here, right? But generally you'll get an upper bound on error. This is less than equal to. You will not get exactly equal to the error. This is a very special case. Okay, so this is the idea behind the error in trapezoid rule and midpoint rule. Okay, so let's do an example now. We have 1 to 2 dx over x is ln 2. So trapezoid rule and midpoint rule can be used to approximate this. That's fine. Estimate the error in trapezoid rule and midpoint approximation of this integral by using n equals to 10 interval. So we are not finding, but we are just approximating it. All right. So let's approximate this using what? The trapezoid rule. So how do we go about it? Again, we'll have n is 10, a is 1, b is 2. So now we need what? K. So for that we need second derivative. So f prime x is 1 over x. F double prime x is minus 2 over, sorry, this is going to be f prime x is 1 over x and f double prime x is going to be minus. Okay, sorry. So f prime x, so f of x is 1 over x. So f prime x is minus 1 by x squared and f double prime x is 2 by x cubed. Okay, so this is your f double prime x. So now what is your k? So f double prime x is 2x cubed, which is, because it's positive, it's 2x cubed, and on 1 to 2. Now think about on 1 to 2. 1 to 2, this is a decreasing function, so it is again bounded by what? 2, right? Since why? Because since 2 by x cubed is maximized, or it's a decreasing function, is a decreasing function, right? On 1 to 2. So the largest value will be achieved when x is 1. So largest value is achieved when x is 1. So now what are the errors then? So suppose if I use trapezoid rule, then we get this is going to be less than equal to k times b minus a to the power 3 by 12n cube, 12n square, which is going to be 2 times 2 minus 1 cube divided by 12 times 10 square, which is going to be 1 by 600, right? So that's pretty good approximation. Similarly, you know that you can actually see that error in this is basically half the error in ET, right? Why? Because, well, you can see that this is 12 and you get EM by multiplying ET by half. So if you multiply, you get this, which is going to be 1 by 2 times 1 by 600, which is 1 by 1200. So you get trapezoid rule. So if you use trapezoid rule, so what is the meaning of this? If we use trapezoid rule, to compute 1 to 2 of 1 by x dx, which which doesn't need log, without using logs, we will get, what we'll get? We'll get value of ln2, whose error is less than 1 by 600. That's a wow, right? Indeed, right? So same way you can do for the other ones as well, right? So similarly, you can compute the other ln, say you can compute 1 to 4 of 1 by x dx, which is going to be ln4, or so on and so forth, right? So you can use trapezoid rule and get the error, which is very close. Now let's look at the following example. Use midpoint rule with n equals to 10 to approximate the integral 0 to 1 of e to the power minus x squared. 1. Give an upper bound for the error involving in this approximation. How large do we need to choose approximation mn to integrate this part so that it's accurate up to 0.0001? So compute, so we have what? N equals to 10. So we have, in this case, delta x is b minus a by 10, which is going to be b minus a by n, which is 1 minus 0 by 10, which is 1 by 10. Now note that this, we don't know how to compute this at all right? So you should understand the beauty of this. Why are we doing this? We have no idea or no way to compute this, right? This function has no elementary antiderivative. So we get this guy, which is 0.1. So we get x1 bar is what? So we have 0, 0.1, 0.2, 0.3, so on, right? So we are taking the midpoint. So what is the midpoint of this? 0.5, right? So x1 bar is 0.5. x2 bar is midpoint of these two guys, so which is 0.15. x3 bar is 0.25, so on. We have x10 bar is 0.95. So we get m10 is delta x times f of x1 bar, f of x2 bar, dot dot dot, f of xn bar or x10 bar. So this is, sorry, 0.05. Okay. And then you keep on doing this. And in the end, you see that this is going to be 0.1 times e to the power 0.05 square plus e to the power 0.15 square all the way to power minus 9.5 square. And I'm using the calculator to do this computation. I get 0.7471 approximately. Yep. Now I want to basically see what is the error in this. Like if I use this, what error did I get in this setup? So again, for B, I need to basically, to find out error, recall we have error is bounded by k times b minus 8 cubed by 24, my bad, 24 n square. So what do we get? So this is, so b is 1, a is 0, n is 10. So we get, and now we need to find out k, right? So take f prime x, which is going to be, so your f of x is what? Your f of x is e to the power minus x square. F prime x is derivative of this, use chain rule, e to the power minus x squared times minus 2x. And f double prime x, here we have to use the product rule. So this is going to be e to the power minus x squared with a minus sign times 2 plus derivative of this is already computed. So we get minus e to the power minus x squared, 2x as it is, from the derivative of this guy multiplied by another minus 2x. So we get e to the power minus x squared times 4x squared minus 2. So now we want to see, so this is maximum. What is the maximum of this guy? The maximum of this guy is x equals to 0, right? And maximum of this guy is x equals to 1. So we have 1 times 2. So therefore, f double prime x is going to be less than equal to 2. Yeah. Note that there are better analysis than this, but we have f double prime x is less than equal to 2, which is your k. So put that there. We get em is going to be less than 2 times 1 minus 0, which is 1, to the power 3 divided by 24 times 10 square, which is going to be 1 by 1200. So this is an approximation. So if you do this, this is an approximation. This is the error you will get, which is really small, right? Which is like 1 over 1,000, which is around 1 over 1,000. So you get 0.001, kind of close to 0.001, right? Error. So at least 2 digits will be the first 2 digits after decimal place will be equal. Now, next question is, how many n do we need to choose so that the approximation mn is accurate up to 0.0001? So how do we go about it? What are we asking here? We are asking that we want em to be less than equal to 0.00001. How many n's do we need? So what do we need? We need em, the error in the midpoint rule, to be less than equal to 0.00001. There were 4 zeros, right? So we get, but what is my em? Em is 2 times 1 minus 0 cube divided by 24 n square, and that has to be less than 0.0001. So we get what? We get 1 by 12n square is less than equal to 0.0001. So now we get what? 1 upon what? 1 upon 12 times 0.0001 is less than n square. And when you compute this, therefore, n turns out to be greater than equal to square root of this guy, square root of this, times 0.00001. Let me run my calculator on this, and you will see that this is roughly, this means n is greater than equal to 9.91.28. So you get n equals to 92 or larger, will give you the answer. Yeah. So if you choose 92 or greater than that, you will get error less than 0.0001. Yeah. So note the following. So the beauty of this process is many times in real life scenario application, you need to compute the integrals. Yeah, you have already seen the physical significance of integral when you were doing area under the curve, for example, or when you connected it with given velocity, how to find the position vector. And there are many other applications, for example, arc length of the function. Yeah, along with other applications in finance and so on and so forth, right? Because after all, integral will compute the average rate of change. So when you're interested in average rate of change of functions, sometimes your function f of x is not given in this nice format here. In fact, it's given by a bunch of numbers, not even as f of x equals to something. It will be given, values will be given at different points. Those are called data points. At x, you will be given f of x. And from there, you are asked to compute the average rate of change. So this is the one of the techniques you use to find out the average rate of change. All right, so now next approximation is approximating using parabolic segments. So instead of basically making trapezoid and stuff like that, we do the following. So let f be a continuous function on a closed interval ab. Divide ab into even number of intervals of equal length. Delta x is again b minus a by n. And these be the endpoints. So x0, x1, x2, x3, blah, blah, blah. Now what you do is the following. Let pi be the point xi f of xi. So now for each I less than n, we approximate area under the curve over the interval xi to xi plus 2. So you are going to go from here to here, okay, 2 at a time, and you will find a unique parabola. So when you go 2 at a time, you're given the function value at x0, you're given the function value at x1, you're given the function value at x2, right? So given a 3-point, you can always find a unique parabola passing through it. So here is one parabola. It's unique parabola which will pass through it. Yeah, it's given by a quadratic equation. So this is a parabola. Similarly, between these points, you can x2, x3, and x3, you can also get another parabola, which will be right. And then you find out area below the parabola. So let's see, how do we do this? So when you do this parabola, you will approximate area. When the parabolas are integrated, it will give you the following formula. Unfortunately, I'm not proving it, but you can prove it. So this is related to what is called as Gaussian quadrature in the analysis, in the numerical analysis discussion. So the formula turns out to be delta x by 3 times f of x naught and f of xn as it is. The endpoints are like that. Then every odd ones are multiplied by 4. You see, every odd one will be multiplied by 4. And every even one is multiplied by 2. So each one of these are multiplied by 2. Okay, so this gives you a Simpson's rule. All right. So the proof of this is based on Gaussian quadrature with 3. We will ignore that for now. Let's use this formula again to see A, how to get an approximation, B, on what will be the error in the approximation. Because our real game here is to find out approximation for integrals, right? So again, for that, notice 0 to 3 dx upon 1 plus x to the power 4. And use this, approximate this by using Simpson's rule with n equals to 6. First of all, note, you cannot integrate this directly. Yeah, there is no integral of this. Yeah. So in this case, when I want to use trapezoid rule, what is my delta x? My delta x is going to be 3 minus 0. Let me erase this so that you can see 3 minus 0 divided by 6, which is 1 by 2, same as 0.5. What are my points? X0 is 0, x1 is 0.5, x2 is 1, x3 is 1.5, x4 is 2, x5 is 2.5, x6 is 3. So now what does trapezoid rule, Simpson's rule tells me? So I'm calling it as 6. Delta x by 3, which is going to be 0.5 divided by 3. Then the end values of the function as it is. So I'm going to write 1 upon 1 plus 0 square and 1 upon 1 plus 3 square. Sorry, it's power 4, right? So 0 to the power 4, 3 to the power 4 as it is. Then what you do is 4 times the odd ones. So 4 times 1 upon 1 plus 0.5 power 4. Then 2 times 1 plus 1 square, 1 power 4, my bad, plus 4 times 1 plus 1.5 to the power 4 plus, let me finish this, write this completely, plus 2 times 1 plus 2 to the power 4 plus 4 times 1 plus 2.5 square power 4, my bad again. So this is 2, this is 2 to the power 4. And then we have again plus 2 times. So we got 4, 2, 4, 2, 4, and then the last one is will be as it is 1 upon 1 plus 3 to the power 4. And then when you find this value, it's going to be 0.98. So this is an approximation for this integral, which we don't know what the value is. Now let's investigate what is the error bound in this. Okay. So error bound in Simpson's rule is actually based on the fourth derivative. So if f to the power, if the fourth derivative of x is less than or equal to k for all x in a, b, then the error in Simpson's rule is given by es is less than or equal to k, b minus a to the power 5, 180 n to the power 4. Now, if you compare this with b minus a cube upon 12n square, or k times b minus a cube upon 24n square, you see that the number below is much bigger here compared to this. So that means it seems that Simpson's rule is better in approximation. That means with lesser number of iteration, you will get a better approximation because the error will become smaller. So let's deal with this problem now. How large should we take n in order to guarantee that this Simpson's rule is accurate within 0.001? Have we done this problem, similar problem? We have done this problem, similar problem here when we dealt with, when we used the trapezoid rule to find out, and the midpoint rule. And we saw that in a trapezoid rule, how many, oh, we didn't compute that, did we? We should have computed how many iterations does it takes. So let's investigate this now. How many iterations will Simpson's rule take to get to that accuracy? Okay, so let's just deal with that here. So how many, so E of S is bounded by 0.000. How many zeros are there? 3 zeros, okay. That is same as K B minus A. So 2 minus 1 to the power 5 divided by 180 n to the 4, and we want this to be less than or equal to 0.0001. Now what is my K? So K, I need to compute fourth derivative of this. So second derivative we already computed for this guy. It's going to be 2x to the power minus 3. Third derivative is going to be minus 6x to the minus 4, and fourth derivative, I will use this now, is going to be 24x to the power minus 5. Yeah, and on 1 to 2, the smallest value is what? Is maximum when x equals to 1, right? Why? Because, well, it's a decreasing function, so the value is achieved at the start of the interval. So this is going to be less than or equal to 24. So this is your K. So you plug it back here. So 24 divided by 180 n to the 4 is going to be less than 0.0001. So we get n is going to be n to the 4 is going to be greater than 24 times 180 times 0.0001, which is roughly 13.130 1033.3. So therefore we get n is greater than equal to 6.0428. Now, so n has to be greater than 6 for sure. So, but n cannot be 7. So since n cannot be odd, why? Because that's the definition of Simpson's rule, right? You divide into even parts. So n cannot be odd. Therefore, n equals to what? 8. Yeah, and this is important. This is key point to remember.